All right, so here we have algebraic rules for limits. And so if we follow these, we can find limits fairly easy in some cases. So we have the constant rule. So the limit of a constant is basically that constant. So if we have a limit of, say, 5, as x approaches c, then that's equal to 5. So where c and k are both constants. Then we have the sum rule. So the limit of a sum is basically the sum of the limits. And so we can split it apart. So we have this limit of f of x plus g of x. Well, we can split that into the limit of f of x plus the limit of g of x. And again, they're both approaching c, which is some constant. And so we can solve this one, and then we add it to whatever we solve that one for, and then we can add them together and get the actual limit. Now we have a constant multiplier rule. Now the limit of a constant times a function is the constant times the limit of the function. So basically, if we're taking the limit of k times f of x as x approaches c, we can pull that k out in front and say, well, k times the limit of f of x as x approaches c is going to be the same thing as if we just had that k there. Okay, again, c and k are constants. Now we have a replacement rule, and so this one is for polynomial functions. So if f is a polynomial function and c is a real number, then what we can do is say, well, we just plug in c into that polynomial function, and then the limit of f of x as x approaches c is equal to that f of c. Now we'll see here in a little bit, we have another one, another replacement rule, but it's for rational functions. So a little bit different. So the next one's a product rule. So the limit of a product is the product of the limits. And so if we have a limit of x approaches c of f of x times g of x, we can just split that into the product of the limit of f of x as x approaches c times the limit of g of x as x approaches c. Okay. Then we have the quotient rule, which works kind of like this. And so instead of a product here, we have a quotient, and we can split those apart as a quotient of the limits. So we break apart the limit of f of x over g of x as the limit of f of x divided by the limit of g of x as they both approach c. Okay. Now the key here is g of x cannot equal 0. Okay, the limit of it. Okay, because if we do, can't divide by 0. Now, the replacement rule for rational functions, so if it's a rational function and c is the valid input for f, then we can say, okay, well, the limit of f of x as x approaches c is equal to f of c. And then one that really helps us out is called the cancellation rule. And so if the numerator and denominator of a rational function share a common factor, then the new function obtained by algebraically canceling those common factors out has all the limits identical to the original function. So basically, if we can, cancel something out on numerator and denominator, then whatever the resulting thing is, that has the same limits as the original function. So what we're going to do here is kind of algebraically determine the limits. So we're going to think about, okay, well, what does this tell us? Well, we're taking the limit of f of x divided by g of x as x approaches 1, and we want to be, or we're given, I should say, the limit of f of x is equal to 6 and the limit of g of x is equal to 3 as both x approaches the point 1. Well, what does that look like? Well, that looks like a limit of a quotient. And so what we can do is we can say, well, this is then the limit of f of x as x approaches the 0.1 divided by the limit of g of x as x approaches 0.1. Well, the limit of f of x, they say, well, that's 6. The limit of g of x, they say, is 3. 6 divided by 3, well, that's 2. Okay, so we used that quotient rule, and we were able to split it into the limit divided by the other limit, and we just plugged in the values they gave us, and we have it. Now this one, well, this one we could do several things. We could factor out a 2, and then after that we could plug in the 0.5 and get our value, or we can just do a replacement and say, okay, well, let's say the limit of x approaches 0.5 of the 10x squared plus 8x plus 6 is equal to basically 10 times 0.5 squared plus 8 times 0.5 plus 6. And again, this is just, where is it at? replacement. So we're just plugging in c into f of x. And so it's either for rational or for the polynomial. And we're doing kind of a polynomial here. And so basically we're going to have, now we have that, and I'll just do this on my calculator on my desk. So we have 10 times 0.5 squared, and then plus 8 times 0.5 plus 6, and that gives us 12.5. Okay, and I'll assume you can plug that into a calculator and not actually show you how to do that on yours. Okay. Now the next one, here we have a polynomial over a polynomial, a binomial. And so if we think about that, we can't really do what we did here because -3, if we plug that in, we get 0 down here. So we have to think about something else here. So I think what we need to do is we need to look at our numerator and see if we can factor that. Well, can we factor that? That's going to be two binomials that come out. It's going to be t and t. It's going to be a plus and minus. So what two factors of 21 subtract to give us 4? Well, 3 and 7, 3 times 7 is 21, and 7 minus 3 is 4. So if we have a 7 here, that'll give us a negative. If we have a 3 here, that'll give us what we need. Now notice t plus 3 cancels t plus 3. And so we've canceled, we've first factored, then we've canceled. And so now we have the limit as x approaches -3 of t minus 7. Well, now we can do the replacement, and that's going to be a -3 minus 7, and that should give us a -10. And so that would be the limit for this one. Okay, so we had to first do the factorization, then cancellation, and then substitution. All right, so this one is also something similar. Algebraically evaluate evaluate the expression and then answer the questions. So we have kind of a two-piece thing here. We have 2x squared when x is less than 0, and so it's going to have a part due in one place, and then it's going to be equal to 4x, which is going to be a linear part here. So this is kind of a parabolic part, and then this is a linear part when it's greater than or equal to 0. And so what we need to do is find the limit of f of x as x approaches 0 from the left. Well, if we think about that, if that's 0, if we're approaching 0 from the left, that's going to be a negative number. Well, that's going to be what we have to do here. So we're going to have to use that top part. So we have to plug in the 0 going from the left, and that's basically going to give us 0, because it's going to be, if we want to do it all the way, it's going to be equals, and then let's see, erase that equals there. It's going to be 2 times 0 squared is equal to 0. So that's what we've done basically. Okay. Now what about from the right? Well, from the right, that's going to be coming from this direction. Well, that's positive over here. So from that side, it's going to be the second part. So that's going to be equal to 4 times 0, which is 0 as well. Okay. So the first part was 0. The next part was 0. And so the next one says, what is f of 0? Well, that has x is equal to 0. The only part where x is equal to 0 is when we have x is greater than or equal to 0. So we have the 4 times 0, and that's 0. Okay. And so what we see is then the limit of f of x as x approaches 0 is equal to 0. That's going to be a key thing. And we see that f of 0 is equal to 0. So we have that this exists. We have this limit is equal to this. And we have that is the same thing as what f of 0 is. So is it continuous? Well, it meets all three pieces. We have the limit. We have f of 0 existing. And that f of 0 is equal to that limit. So yes, all three conditions are met. Okay, and so it is continuous. All right, so that's all I have for section 1.3.